Have you ever found yourself just staring at one of those gigantic, incredibly bright video walls and wondering how in the world does that actually work? How do millions and millions of tiny points of light come together to make one perfect seamless image? Well, let's get into it, because the answer is smaller, more complex, and frankly, way more fascinating than you might think. Right. So behind every vibrant color, every smooth motion on a digital screen, whether it's in Times Square or your local sports arena, there are literally millions of unsung heroes all working together perfectly. And we're talking about the individual lights themselves, the absolute building blocks of every image you see. And that's what this explainer is all about, the LED package. This tiny little component is the real heart of any LED display. Its design has gone through this huge evolution, and that evolution has completely transformed the screens we look at every single day. To really get what's going on with this evolution, we've got to speak the language of light first. There are a couple of key ideas we need to wrap our heads around before we can truly appreciate the differences in all this tech. First up, we've got luminous flux, and we measure that in lumens. The easiest way to think about this is as the total raw power of a light source. It's all the light just pouring out of that LED in every direction. It's kind of like the horsepower rating for an engine. It's just a fundamental measure of its total output. But what we actually see as brightness, that's measured by luminous density in candelas per square meter, or nits, as you'll often hear. So think of it like this. Raw power is one thing, but nits measure how much of that light is actually focused on a surface and looks bright to our eyes. This is the one that really matters for the viewing experience, because it turns raw light into the brilliant screen we actually see. All right, so with those terms in our back pocket, let's talk about the technology that has been king of the hill for years, SMD, which stands for Surface Mount Device. This technology took over from an older, clunkier tech called DIP, and it pretty much revolutionized the whole industry. So the idea behind SMD is really simple. As you can see right here, inside each of these tiny packages, you've got 3 separate little LED chips, one red, one green, and one blue. By controlling how bright each one is, you can mix them together to create pretty much any color you can imagine. This simple 3-in-1 design became the bedrock of the modern digital pixel. And for a long time, SMD was the perfect solution. But technology never just sits still. So what happens when you need screens with pixels so close together that they're basically invisible, or screens that need to be tough enough to get bumped or even touched? Well, that's where the physical design of SMDs starts to show its weaknesses. And that question leads us directly to the next generation of packaging, which was really driven by this need for higher resolution and way more durability. So let's meet the 2 big contenders, COB, which stands for Chip on Board, and MIP, or Micro in Package. They're both trying to solve the same problems, but they go about it in totally different ways. And this slide just shows you the physical difference perfectly. On the left, that's the traditional SMD module we were just talking about. See how it's kind of bumpy? Each individual pixel package is sitting right on top of the board. Now, look to the right. That's the new way of doing things. It's completely flat, totally seamless, and this isn't just about looks. It's a huge change that makes the screen surface way more durable and visually consistent. So what was pushing this change? Well, exactly this stuff. The industry wanted to pack pixels tighter for higher resolutions, and they needed screens that could take a hit. But it didn't stop there. They also wanted deeper blacks for better contrast and much more uniform color. This is what pushed us from 8-bit color, with its millions of shades, to 16-bit color, with trillions of shades. That jump gets rid of ugly color banding and gives you those perfectly smooth gradients. These were the demands that paved the way for COB and MIP. Okay, now this is where things get really interesting. COB and MIP are both next-gen technologies, for sure, but they are not the same thing. Each one has its own set of pros and cons, which makes them better for different jobs. So let's put them head-to-head. Let's break this chart down. You can see there's a clear trade-off here. If you want maximum energy efficiency and the absolute best contrast ratio, we're talking the deepest, inkiest blacks possible from that seamless surface, then COB has the edge. But if what you need is perfect white color consistency, which is absolutely critical in something like a broadcast studio, well, MIP is better. And just look at the bottom. MIP's design makes it way better for building huge, seamless video walls and gives it this incredible flexibility for all sorts of different uses. And really, that flexibility is MIP's killer feature.
It can be used to make screens with a superfine pixel pitch of just 0.4 millimeters, all the way up to 4 millimeters and even bigger. What that means is the same core technology can be used for basically everything, from a high-res indoor broadcast set to a massive outdoor rental screen. So how do they even make this stuff? The MIP process is pretty clever. As you can see, it all starts with a mass transfer of these tiny little LED chips. Then they get packaged and sliced into individual pixels. But here's the key step. Each one of those tiny pixels is inspected and color matched before it ever gets put on the final circuit board. This pre-calibration is the secret to its consistency. And then finally, a protective coating gets applied to make it durable.
So after all that, who wins the duel? Which technology is better? Well, the answer isn't quite that simple. The future of LED displays isn't about one winner takes all. It's all about being adaptable. The big takeaway here is this. COB and MIP are going to continue to exist side by side. There's no single best technology. The best choice is always going to depend on the specific job. Is it an indoor screen where contrast is king? COB might be your answer. Is it a gigantic, flexible outdoor display that needs perfect color matching? Then MIP is probably the way to go. But here's the thing. No matter what tech we're talking about, SMD, COB, or MIP, they all share one common enemy: heat. Getting that heat away from the electronics is, you could argue, the most critical factor for the long-term health of any LED screen. The tighter you pack those pixels for higher resolutions, the more intense this heat problem gets. Solving it is a massive engineering challenge that ultimately decides how reliable that display is going to be. In the end, it really all boils down to this. The market is going to decide. As the manufacturing costs change and new demands pop up, the balance is going to shift. The winning technology will be whichever one gives us the right mix of performance, reliability, and price for whatever the world wants to build next. So as these technologies keep getting better and the costs keep coming down, it leaves us with a really fascinating question. With pixels becoming smaller, tougher, and more efficient than ever before, what new kinds of screens are going to be possible in the next, say, 5 or 10 years? Are they going to be transparent, flexible, completely built into the buildings around us? I mean, one thing's for sure. The evolution of this tiny little package is what's going to define the visual world of our future.